Imagine a bridge in a steady wind. Instead of staying still, it starts twisting wildly, building up until it collapses. How can a constant force create an ever-growing disaster? We'll crack this mystery. We just saw a bridge wobble dangerously. To understand that motion, we need a translator. The Laplace Transform is a math tool that swaps the variable of time for a new variable of complexity, turning tough calculus problems into simpler algebra ones. The key is the new variable, s. It's not just a regular number. S is a complex number, meaning it has a real part for exponential growth and an imaginary part for oscillation, all packed into one symbol. We call it a transform because it moves the whole problem from the time domain into the length domain. It's like translating a tricky sentence into a language where the puzzle is much easier to solve than translating the answer back. We just saw the translator. But why bother? Because in the time domain, calculus is a tangled mess. Derivatives and integrals knot together, making simple systems hard to solve. The Laplace transform slices through this knot. It magically turns derivatives into simple multiplication and integrals into division. That tangled swing equation becomes a basic balancing act you can solve by rearranging. We just saw why we need a translator. Now, let's see it in action. The Laplace transform takes a story told in time, f, t, and rewrites it in a new language based on a variable s. Imagine a signal that decays over time. On the left, we see it in its original form. The transform places its essence into a new shape on the right, making hidden properties, like stability, instantly visible. This new language's power is its simplicity. In the S-domain, the calculus of time, derivatives and integrals, becomes basic algebra. We can solve tough problems using just multiplication and division. We just saw the translator needs input. That input is a function of time, written f, t. Think of it as a movie, time t runs forward, and f, t, is what you see on screen at each frame. Imagine tracking temperature over a day. At 6 a.m., t equals 6, it is cool, f, 6, is low. By 2 p.m., t equals 14, the sun has done its work, f, 14, peaks. The curve connects every moment into one story of change. A car's speed is another f, t. Cruising at a steady 60 km per hour gives a flat line, f, t, never changes. But if you accelerate from a stop, the line rises, f, t, grows as t grows. Both are valid scripts for our translator. We just used functions of time. Now, the translator's magic key is a new variable, s. It's not just one number, but a two-in-one complexity number that can twist and shrink signals. Picture a 2D map, the S-plane. Every point on this plane is a different s. Sliding left dampens signals faster, sliding right makes them grow. Moving up and down changes how fast they oscillate. The translator multiplies our time function by e to the minus st. This factor acts like a shrinking, spinning probe. It spirals inward, testing if our signal matches its specific pattern of decay and wiggle. We just met s, the complex frequency. Now let's see what st actually looks like over time. Break it apart, the real part, sigma, makes it grow or shrink. The imaginary part, j omega, makes it spin, a sine wave. First, set the spinning part to 0. When s is just a real number, st is a simple curve. A positive s gives decay, the function shrinks, weighing the past less. A negative s gives growth, amplifying the future. Now, set the real part to 0. With a purely imaginary s, the exponential becomes a pure oscillation, a sine wave that never decays. It's like a tuning fork, ringing forever, weighing each moment equally but with a phase. We just built our exponential probe. Now we combine them. The Laplace transform is a continuous sum, an integral, that multiplies our function f of t by e to the minus st, and adds up the result from 0 to infinity. Let's see it for a fixed s, say s equals 2. We graph our function f of t and our decaying exponential e to the minus 2t. At every instant t, we multiply their heights. This new curve is the weighted signal. Now we find the area under this product curve. That single number is f of s for s equals 2. We repeat this process for every s in the s-plane, building a complete new picture of our signal in the s-domain. We just defined the Laplace transform. Now let's use it on the simplest function, f of t equals 1. We multiply by our translator e to the minus st, and find the total area from 0 to infinity. The area up to some time t is 1 minus e to the minus st, all over s. As t marches to infinity, that exponential term must shrink to 0 for the area to be finite. This requires s to be positive. The total area simplifies beautifully to 1 over s. Watch what happens as we change s. A larger s means the curve decays faster, so the area shrinks. This relationship is our transformed function, plotted on the s-plane. We just transformed the constant 1. But 1 is just e to the 0 times t. Now, let's give it a growth rate. If a is positive, it grows; if negative, it decays. We multiply our translator kernel e caret st by the function e caret at. The exponents add, giving us e to the as t. Now we integrate this combined exponential from 0 to infinity. This improper integral only converges if the exponent is negative, meaning it decays to 0. That requires s to be greater than a. The translator's damping must outrun the signal's growth. Evaluating the integral gives the beautifully simple result, 1 over s minus a. This function blows up at s equals a pole. The transform exists only to the right of this pole, in the region of convergence. We just transformed a growing exponential. But what if our signal is a sum, like e caret at, plus a constant? Let's see what the translator does. The integral, our continuous sum, splits right down the middle. The transform of e caret at plus 1 is just the transform of e caret at plus the transform of 1. No tangled mess. This is linearity. It means we can smash a complicated signal into simple building blocks, like exponentials and constants, translate each one, and just add up the answers. No heavy lifting. We just saw linearity lets us split sums. To transform sine and cosine, we first rewrite them using Euler's formula, a bridge from circles to exponentials. Solving for each gives cosine as half the sum of two spinning arrows, and sine as half their difference. We know the transform of a single exponential. By linearity, we transform each piece separately. For cosine, plug in a equals j and a equals a j, then add the results. A common denominator reveals a clean, real expression. The denominator s squared plus squared vanishes at s equals j and s equals a j. These poles, the roots, lie on the imaginary axis. This tells us sine and cosine are pure, undying oscillations, with zero real part to cause decay. We just transformed sine and cosine. But the real goal is solving equations full of derivatives. If we can transform a derivative, we turn a calculus problem into a simple algebraic one. We start with a definition of the transform, applied to f' of t. The tool to crack this open is integration by parts, the reverse of the product rule. We choose e to the minus st as our u. Applying the parts formula, the first term evaluates to minus f of 0, assuming the function doesn't grow faster than the exponential decay. The second term pulls out an s, leaving exactly s times the transform of f. Differentiation in time becomes multiplication by s. We just learned how to transform derivatives. Now let's use it on a real problem, a car's suspension. A mass bounces on a spring and a damper resists motion. Newton's second law gives us this differential equation. We transform the whole equation using linearity. The derivative rule turns x into s squared x. Since the car starts from rest, initial position and velocity are 0. The calculus has vanished, leaving pure algebra. Plugging in our numbers, we factor out x of s. The quadratic s squared plus 3 plus 2 appears. Its roots, -1 and -2, are the poles. They already whisper the time solution, 2 decaying exponentials. We just solved a differential equation by finding its poles. Now let's see why those pole locations matter. Every single point on the S-plane is a hidden time signal waiting to be revealed. The vertical axis splits the map. If a pole sits in the left half, where sigma is negative, its signal dies away. That's stability. A pole on the right means a runaway signal that grows without bound. Watch what happens when we drag a pole around. Pulling it left makes the signal vanish quicker. Lifting it higher makes it wiggle faster. Crossing into the right half flips the story, the signal swells instead of shrinking. We just saw how poles map stability. Now, instead of solving messy differential equations by hand, engineers convert entire systems into simple blocks in the S-domain. Take a car on a hill. Its mass and engine force create a differential equation. In the S-domain, we design a controller block that pulls the system's poles into the stable left half plane, so speed stays smooth. Noise-cancelling headphones work the same way. The circuit's job is to create a stable system where the output perfectly cancels the input noise, all designed by placing poles for a fast, non-oscillating response. We just saw engineers use this daily. Let's recap the whole journey. We started with a time signal, multiplied it by a special exponential to tame it, and integrated to land in the S-domain. That one integral gave us a library of transforms for constants, exponentials, and trig functions. The derivative rule was the real magic. It turned calculus problems into simple algebra. We mapped these transforms onto the S-plane. The location of poles, those special S values, instantly reveals if a system will decay and settle, or grow out of control. So a messy differential equation in time becomes a clean, simple expression in S. You solve it with basic algebra, then transform back. That is the whole game. Remember that twisting bridge? A steady wind force F acts on it. The bridge's motion follows y plus y equals F. Taking the Laplace transform turns this calculus problem into algebra. S squared y plus y equals F. Best solve for y to get F over S times S squared plus 1. We break the fraction apart using partial fractions. F over S is the constant wind, its transform gives a steady F in time. Fs over S squared plus 1 is a cosine, it gives F times cos t. Look at the plot, the twist y of t equals F times 1 minus cos t. It swings endlessly between 0 and twice the wind force. With no damping to drain energy, the steady wind pumps the oscillation larger and larger. A constant force creates an ever-growing disaster. We just saw it solve the bridge mystery. Remember this core idea: the Laplace transform swaps hard calculus for simple algebra, and a system is stable only when all its poles live in the left half plane. The most common mistake is ignoring the region of convergence. A transform formula without its ROC is ambiguous. It could belong to two completely different signals. Always pair them together. To never forget the derivative rule, link the letter s to the word slope. A derivative in time is just a slope, and in the s domain, taking a